In this presentation, I will talk about the topic of discovering correlated high utility item sets using a measure called the bond measure. My name is Philip Fournier-Viger. I will present this paper. Okay, so first I will talk about the type of data that we consider. Here I have an example. What we call a transaction database. It is a database of transactions about what some people will buy in a store, for example. So here we have a set of items like A, B, C, D, E, and so on. A, for example, could be apple, B for bread, C for cereal, E for eggs, and so on. So we have many items. And then a transaction, it is a set of items bought by some customer. So, for example, at the bottom you see a table with 4 transactions, T1 to T4. And each transaction is a set of items. For example, transaction 1 is apple, bread, cereal, D, and eggs, for example. So if we have a database like this, we can try to find some patterns in this data, like the people who buy apple always buy the bread, for example. Okay, so to find interesting patterns in the transaction database like this, a popular topic is to find the frequent patterns. Frequent patterns means some patterns that appear many times in the data. So the task of frequent pattern mining was proposed in 1993 by Agrawal basically is very simple. I will explain a little bit. The input of frequent pattern mining is a transaction database and also a parameter set by the user that we call min sup. It means minimum support or minimum frequency. So we want to find the frequent patterns that appear at least min sup times, where min sup, the minimum support, is a parameter set by the user greater or equal to 1. So the output is the frequent item set, the sets of items like bread, apple, that appear together in at least min sup transactions. So I will show you an example. Okay, so we have again the same database on the left. We set min sup equal 2, so that means we want to find all the patterns that appear in at least 2 transactions. And as you can see on the right, we find some patterns like D, E, D and another item E together is bought by 3 customers as a support of 3 or frequency of 3. B, D, E appear twice. So you can see in T4 and in T1 we have B, D, E together. So how to solve this problem about frequent pattern mining? The naive approach to solve this problem is to calculate the frequency of all the possible item sets. So like apple, apple bread, apple cereal, apple bread cereal, and so on. So all the possible combinations of the items that we have in the database. So if there are n items, let's say you have 5 items like A, B, C, D, E, n items, then there are 2 to the power of n minus 1 possible item sets that in the search space. So for 5 items, 2 to the power of 5 is 32 minus 1, so there will be 31 possibility. So this is not that much, but if in a store there are 1 million items, for example, then there are 2 to the power of 1 million possible item sets. So in this case, we cannot use the naive approach, that is to count the frequency of all the possible item set, because it will just take too much time to look at the 1 million, 2 to the power of 1 million possibilities. So how to find the solution to the problem of frequent item set mining efficiently in terms of time or memory? The solution is to use some efficient algorithms that have been proposed before, like a Priori, FP growth, H-mine, LCM, and so on. So let me explain to you how these algorithms work. All of them are based on a special property of the support or frequency that we call the a priori property. It's say if you have two sets of items, X and Y, X is a subset of Y, then the support of Y must be less than or equal to the support of X. So let me explain this with an example, because maybe it's not so clear, maybe. Okay. So if the support of AB is 3, AB appears 3 times in the database, then according to the property, any superset of AB, like ABC, cannot appear more than 3 times, must appear 3 times or less. So if you have AB appear 3 times, you know that all the supersets of AB, like ABC, ABD, and so on, cannot appear more than 3 times. So actually, this makes sense, because if AB appears 3 times, and then you consider ABC or ABD, you add another item like C and D, of course it cannot appear more often than AB, with or without a C or D. Okay. So this property is very powerful, because if you know that AB is 3, and you set the minimum support to 4, then you know that all the superset of AB cannot be the frequent item set. You don't need to look at all these possibilities. So it will save a lot of time. So there have been a lot of algorithms about this, about frequent pattern mining, and many applications in many domains, not just about transaction, about shopping, but it can be used for text mining or other things. So basically, a transaction is a set of symbols, and you can use this to model the words in a sentence or many other things. So frequent pattern mining is useful, but has some important limitations. First, the frequent patterns are not always the most interesting. For example, if you look at the customer data, maybe many people buy the bread and milk together, but bread and milk is not necessarily something interesting. Maybe it just appears often together because many people buy milk, many people buy bread. So they just appear together by chance, actually. Okay. And also, in frequent pattern mining, we don't consider the quantities of items. That means if you buy 5 breads, or 10 bread, or 20 bread, it's the same thing. So in frequent pattern mining, the quantities are 0 or 1. You buy or you don't buy, but we don't know how many units you buy of each item. And also, all items are considered equally important. So for example, you buy 1 bread, or you buy 1 diamond, or you buy something very expensive. It will be all considered the same, because there's no weight to evaluate. There's no way to evaluate how important an item is. So, an extension of frequent pattern mining that avoids this problem is called high utility item set mining. It generalizes frequent pattern mining. It is a more general problem where item can appear more than once in the transactions. So for example, now we know that a customer buys 3 bottles of milk or 10 bottles. And items also have some unit profit. So a bottle of milk generates $1 profit, for example, or a diamond $1,000. And the goal is to find the patterns that have high utility. The high utility means, for example, we want to find a set of items bought together that yield a lot of money. Or if we think about other problem, for the web page, for example, the click on the web page, utility could be the page where the people spend a lot of time, not the money. So it can be different things actually. But here we're talking about the money in my example. So with high utility item set mining, if we look at the shopping data, we can find maybe that many people buy caviar and wine, Not so many actually. It is quite rare, but it makes a lot of money. So in frequent pattern mining, maybe we don't find this pattern, but for the manager of a store, it's a very useful pattern because it makes money. Okay. So let me show you in more detail how it works about high utility item set mining. The input first. It is a transaction database like this, as you can see on the left, with some quantities. Here we have 5 transactions, T1 to T5. The first one indicates A1, that means 1 apple, 5B, like 5 bread, 1C, 1 cereal, and so on. And then on the right, you have a table with the unit profit. So A5, that means 1 apple yield a $5 profit. 1B bread is a $2 profit. 1 cereal, $1 profit, and so on. So we have the data about the transaction with the quantities, and also we have the unit profit of each item. Then the user must set a parameter we call the minimum utility, like minimum amount of money. Then the goal is to find all the sets of items bought together that make at least this amount of money. So what is the output? The output is all the high utility item set. That means the item sets that generate at least the minimum amount of money. So for example, if we set minimum utility to $33, we'll find 4 item set. BDE make at least $33. It makes $36. BCD $34. BCD $40. And BC $37. Okay, so now I did not explain how to calculate the utility of the money. I will explain to you next. So how to calculate the utility? Let's take an example. Look at the item set B, D, E together. Okay, when the people buy B, D, and E together, this is important. It must be together. Okay. So we look at the transactions that contain BDE. It appears in transaction 1 and 2. BDE, BDE. Now what we do? We take the first one. 5 bread, 5 units of B multiplied by $2 each. So 5 multiplied by 2. Then D, 3 units of D, and D is $2 each. So 3 multiplied by 2. Then E, 1 unit of E multiplied by 3, 3 multiplied by 1. Then we do the same for transaction 2. 4 units of bread multiplied by 2. Okay. 3 units of D multiplied by $2 profit. And 1 unit of E multiplied by $3 profit. So total is $36. This is the money for BDE. Okay, so now let me talk to you about how to solve this problem. Okay, so there's one challenge I did not show in the PPT here, but it is that if you have an item set like BDE, the superset of BDE can have the utility that is lower, higher, or equal to the utility of BDE. That means if you have BDE is $36, the superset like BDE and C maybe can have the utility lower, higher, or equal to BDE. So this is very strange, okay? But why? Because if you add more item to BDE, maybe it will add some money. But if you add more item, you have BCD, then maybe BCD appear less often than BDE. So because of this, it can also make less money. So it depends. So because of this, we don't have the a priori property like in frequent pattern mining. It's more difficult to reduce the search space to find the patterns more quickly. So how to solve this problem? There have been several algorithms like two-phase, FHM, FIM, and so on. The key idea is the following. Since the utility is not anti-monotonic, we use some upper bound on the utility that respect the a priori property. So, although the utility is not anti-monotonic, we don't know it will increase, decrease, or stay the same. we can find some upper bound that will have the a priori property, and then we can use them to reduce the search. So here I will not explain the details about the upper bound because these upper bound have been proposed in the previous paper. In this paper I will talk to you, we'll extend the FHM algorithm actually. So we'll use the same upper bound, but we will add also some other things that I will explain. Okay, so high utility item set mining is very useful. We can find the patterns with high utility or money. But there is a problem. It is useful to find the patterns profitable with a lot of money, but it can discover some item set that are weakly correlated. So for example, if you think about bread and caviar is some kind of food from the fish, like eggs. Okay, it's very expensive and not so frequent. So if you put bread with caviar, maybe it has a high profit. But why? Maybe only because caviar makes a lot of money actually, and bread, everybody buy the bread. So maybe they just appear together by chance. So most of the time people buy the bread, they don't buy the caviar. But sometimes they are together and make a lot of money. So actually we can find this pattern as a high utility item set. But the correlation between this item, there's no correlation, there's no relationship between these items. So it is not a strong pattern and it is not interesting actually. So there have been some paper about correlated pattern mining and some paper about high utility item set mining. And here we want to combine these two ideas to find the pattern that makes a lot of money, but also the items are strongly correlated together. Okay, so let me explain a little bit more about this. So how to detect if items are correlated? There are several approaches. One approach is to use some statistical test to find the productive item sets, for example. So this is interesting because we use statistical tests, but actually it's very costly. It takes a lot of time to calculate. And there are some measures that are quite good and very easy to calculate, like the affinity or the bond measure. So in this paper we had to choose. So we decided to use the bond measure here. Okay, so how we calculate the bound of an item set is quite easy. I need to introduce two concepts. What we call the conjunctive support of an item set X is the number of transactions that contains X. So the conjunctive support of AB is the transactions that contain A and B together. How many transactions? Okay. Now a new concept is the disjunctive support of an item set X. So if you have an item set X like AB, the disjunctive support is the number of transactions that contain at least one item from AB. So the number of transactions that contain A or B or AB together. Okay. So the bound of an item set X is the conjunctive support of X divided by the disjunctive support of X. So let me explain this again. The bound of an item set X is how many times all items of X appear together divided by how many times at least one item of X appear in a transaction. So if this number is close to 1, that means the items always appear together, or most of the time. And if this number is very small, close to 0, that means the items in X are not strongly correlated together. So it is a very simple measure to calculate, and it can be used to find the correlated patterns. So there's a property I put on the bottom. It is that the bound measure is anti-monotonic. So if you have two items set X and Y, X included or equal to Y, then the bound of X must be greater or equal to the bound of Y. So I will not do the proof. if you're interested, you can read the paper also. Okay, so we define a new problem in this paper to find the correlated high utility item set. That is, the item set that have a utility no less than a threshold, the minimum utility, and a bound no less than a threshold, the minimum bound. So I show you an example. We have a database again. I think it is the same database. And if we set minimum utility 30, minimum bound to 0.5, we find the result at the bottom. So BCE, the bound is a 3 because 3 times BCE appear together. Divide by 5 because in the 5 transaction at least BCRE appear. Okay, so the bound is 0.6. So that means it is somewhat correlated. Now BE has a bound of 0.75 because that means it is more correlated than BCE actually. So 3 out of 4 times these items appear together. So this is a strong correlation. Okay, so now I explain the main idea what we want to do. Okay, correlated high utility patterns, that's what we want to find. So I want to give you the main idea about the algorithm. I will not explain all the details because it will take quite some time, but I want to give you the main idea. If you are interested, you can always also read the paper, and the code of our algorithm, the database we use in the experiment, are all available in our SPMF software. I will tell you again later. Okay. So the FCHM algorithm, it is an algorithm to find a correlated high utility item set. It performs a depth first search. So here you see the picture. We have the kind of tree. This is the search space. All the possible item set with A, B, C, D for my example. So on top you have the empty set, then you have A, B, C, D. Then A and B together, AC together, AD, BC, and so on. You have all the possibilities. So the algorithm will do a depth first search. It starts from empty set, then A, then AB, ABC, ABCD, then go up, ABD, then go up, AC, ACD, and so on. A depth first search. Now, as the other high utility item set mining before, we use the upper bound on the utility to eliminate some possibility. So when we do the depth first search, we are at A, item set A. We calculate an upper bound on the utility of A to decide, do we need to look at the extension of A, the subtree, what is below A, like AB, AC, and AD. So again, the upper bound on the utility is not something new in this paper. We extend the FHM algorithm we had designed in previous work. So I will not explain this part because it's not new in this paper. Okay. Now the main challenge, it is how to calculate the bound of an item set. This is the novelty in this paper. Okay. So the FHM algorithm is inspired by the FHM algorithm for high utility item set mining. So each item set will be annotated with a table we call the utility list. In this table, we have the information to calculate the upper bound on the utility. So this part I will not explain again. I will assume you are familiar with FHM. Now, what is new? We store for each item set X a new structure we call the conjunctive bit vector. It is a vector of bit, a list of bit like 0 and 1. And this store the union of all items in X. Okay. So let me explain this to you with an example. So the conjunctive bit vector of D, for example, it is transaction 345. That means D appear in 345. And we can encode this as a bit with 0, 0, because we don't have T1 and T2. Then 1, 1, 1, that means T3, T4, T5. And a 0 for T6, because D does not appear in T6. Okay. So similarly, we have the bit vector of the conjunctive bit vector of AC, T1, T3, T5, T6. That means in this transaction, at least A or C or AC together appears. So again, we can encode this as a bit vector. We have the first bit set to 1, which means that it appears in T1, not in T2, then T3, not in T4, T5, T6. So we have 6 bits for the transaction from T1 to T6. So to calculate this vector for the single item like A, B, and C, we can scan the database to calculate this. And for the other item set like ACD, to find the vector, we can combine the vector of, for example, AC and AD, the subsets. So we don't need to always read the database to calculate this vector. And using this bit vector, we can very quickly calculate the bound. Okay. So here in my PPT, my presentation, I did not explain so much about the details, but the main idea, for each item set we have a vector, and if we have some item set like A and C, we can combine together and get the vector of AC, and then we can calculate the bound directly for AC without reading the database. Okay, so there's also tree optimization in the paper to calculate more quickly and reduce the search. Okay, some of these novelty, like strategy tree, is about calculating the bound of all pairs of items. So I'm not explaining details. If you want, you can have a look again at the paper. There's also strategy number 4. Okay. So in this paper, we did some experiment on the real data to see the behavior of our new algorithm. So we use for a real database a different number of transactions, different number of items, and different length of transactions. So the goal is to see how the algorithm behaves for different types of data actually. So we use 4 benchmark database. FoodMart is a real database for shopping and retail also. And Mushroom and Kozarac are other type of data, not about shopping, but they are a benchmark database. So, and we want to use different types of data, so we use this database. So in this experiment, we run the FCHM algorithm with different min-bound threshold values to find the more or less correlated patterns. And we compare the algorithm with FCHM that find all the high utility item set, not just those that are correlated. So FCHM will always find more patterns than our new algorithm FCHM. Why FCHM? Is for fast correlated high utility item set mining. That's the name. So let me show you some results. So here we compare the number of patterns found on the 4 database. So there's 4 charts. On the x-axis, you can see the minimum utility, and on the y-axis, the number of patterns that we found. So, and you have FCHM in green, okay, with a diamond shape. That means the number of high utility item set. You can see very high. And then you have the number of correlated patterns. So the high utility item set that are correlated for min bound 0.9, 0.7, 0.5, and so on. So here, for example, if you look at mushroom, there can be more than about 1 million high utility item set. But if you set the min bound to 0.9, you find less than 100 patterns. So that means using the bound measure, you can filter a lot of non-correlated patterns. So actually, it's very useful because these experiments show that in real life, a lot of patterns are not strongly correlated. So actually, it's good to eliminate them. Okay. So again, the min bound parameter can be set in different way, higher or lower, if we want to find more correlated, or we also want to find the less correlated patterns. In terms of execution time, we did the same experiment. We varied the minimum utility and look at the time. And we can see that, again, we have the FHM algorithm, and when we use the bound measure. When we use the bound measure, the minimum bound, it can be up to 100 times faster. So not only we find less patterns, we find the correlated patterns also, but also it will be much faster. It can be 100 times faster. So it's very good, actually, very interesting, I think. Okay, so we did also some experiment about the memory. Okay, so we skip this part. You can have a look if you want. So in conclusion, in this paper we presented a new type of patterns called the Correlated High Utility Itemset, a new algorithm called FCHM with some new data structure and pruning strategy. We did some experiment and we found that our algorithm can eliminate a large number of non-correlated patterns. It can be also much faster than FHM in many cases. And the source code and datasets, if you want to try, you can download the code, our program, all our datasets. They are open source in Java. You can use in the SPMF data mining library. Also, if you want to use another language like Python and so on, it is not difficult to use the library. You could connect with other programming language. It can be used from the command line, for example. So I hope you have enjoyed this presentation. I can show you, this is the website of SPMF. You can have a look if you want. You just type SPMF in your search engine, you will find the website. There's a lot of example, introduction, and so on. So again, I hope you enjoyed this presentation. There are more videos on the website and so on. You can have a look. And that's all for this presentation. Thank you.